Hi, I'm Valerie Brogdon, and I'm here today to tell you about what I've learned in the last few months about neural implants. And this is a topic that's just really interesting to me. I love toying with the concept of manipulating the functionality of our brains with electronics, but I am not an expert here, so please don't grill me. I actually gained exposure to this topic through my work running a lab at the university. So I'll just give you a quick overview of what I do in my lab. So I run a focused ion beam scanning electron microscope lab at the university, and that is a mouthful, so I usually just say FibSem for short. And this is a core facility that provides a scientific service to researchers. So basically, this is a very fancy microscope. You can image teeny tiny things, and you can also cut into them and manipulate them with the ion beam. So this is just a fun movie that I took where I use my ion beam to etch the word hello onto a fly's eye. Here I'm zooming out and zooming out so you can see what it is. I just found this fly on the windowsill in my garage. Okay, and here is an image of a label that I etched onto a strand of my hair. You can read it here. It says, "This is a strand of Valerie's hair." But these are just some kind of silly examples to show you what's possible with a focused ion beam. So people bring me all kinds of samples, and often what they want me to do is cut them open and look inside. So this group of researchers brought me this sample, and it's an array of neural electrodes that were all fabricated in the Knight campus. And the idea with this particular electrode design is that the neurons are supposed to grow inside of these little pores in each device. And these little pyramids here are actually made of a flexible polymer because your brain moves around quite a lot. It's pulsating inside of your head. So if there's some kind of rigid device in there that isn't able to bend and flex along with the movement of your brain, it's going to cause a lot of inflammation and scar tissue that will ultimately wall off the device from being able to interact with neurons, and it will lose functionality. But the challenge is that not only does it have to be flexible and squishy, it also has to be conductive so that it can send and receive electrical signals from your brain. And most flexible materials are not especially conductive. So some groups are working to develop new types of materials that are both conductive and flexible, but this group's solution was to spin a coat of platinum onto the polymer. And they brought me this sample, and what they wanted to know is whether or not they successfully got the platinum inside to line the insides of the pores. So I cut it open with my ion beam, and you can see this bright stuff is the platinum, this dark stuff is the polymer. That's before I cut it, this is after looking inside. And they did in fact get platinum inside of the electrode. So we ended up publishing this work in Nature, and this is a screenshot from our paper. And I was just so fascinated by this sample that I started looking into all the different things you can do with neural implants, and the applications are endless. There are so many intriguing use cases for different types of therapy or even human enhancement. So I started volunteering my focused ion beam expertise for a research group doing neural engineering in the Knight campus just to see what they're up to, and also to hopefully slowly crack away at a PhD on the side of my full-time job running the Fib Lab. And today I've brought Dr. Felix Deku, who is a professor at the Knight campus, and he is pioneering the development of soft, ultra-flexible neural interfaces. And his research focuses on creating ultra-thin, biocompatible electrode arrays that can safely integrate with brain tissue while minimizing scarring and inflammation. So Felix has been letting me hang out and learn more about his work, and I've really enjoyed it, and I'm very excited to learn more. And I remembered this amazing piece of advice that I heard once in a song by an artist called Starslinger. And the advice is study the history of the form that you wish to master. So that's why I'm learning about the history of neural implants. But let's start at the present. So for a lot of us, including myself, our initiation into the possibility of neural implants was hearing about Elon Musk's company's Neuralink, which has brought neural implants into the news in recent years. So Neuralink made amazing strides in developing devices to facilitate the computer-brain interface. Nolan Arwell, pictured here, was the first human recipient of a wireless neural implant that allowed him to control a computer cursor with just his thoughts. So Nolan is a 29-year-old man who was injured in a swimming accident when he was 22 and suffered a severe spine injury that left him paralyzed from the neck down. So he went from being an independent young man living on his own to becoming completely dependent on others to feed him and move him. Nolan loves video games and he loves playing online chess, but until he received this implant, the only way he could manipulate items in the external world was through a mouth stick, poking away at a computer screen. So now he's able to play computer games with his buddies from college. And not only was he able to play them, he could beat them at a game based on speed. So you can imagine what an amazing sense of autonomy this has granted Nolan, and it really highlights some of the best potential capabilities of this technology. However, Nolan was not the first person to control a computer cursor with just his mind, and neural implants have been in use in humans for almost 75 years. And not all of the proposed applications for neural implants have been as helpful or as wholesome as this one. So let's talk about Jose Delgado, who was born in Spain in 1915 and worked as a professor of neurophysiology at Yale University. So he's thought to be the earliest proponent for neural stimulation via electrodes. Delgado had a famous experiment where he was able to change the behavior of a charging bull with some electrical stimulation from a device he had implanted and controlled with a radio transmitter. The device had been implanted in a region of the brain responsible for controlling aggression and motor control. As the bull charged towards Delgado, he sent an electrical pulse via remote control, and the bull stopped mid-charge. Jose claimed the bull was not tamed, he simply lost his aggressive instinct through electrical stimulation. So Delgado did a lot of experimentation with neural stimulator devices on monkeys, and he even did some work on humans. Delgado invented a device that he called the Stimoceiver, which is a device that both stimulates the brain with electrical signal and it records electrical signal from the brain. And this was an early prototype for a lot of the devices that are in use today. And he implanted these devices in humans in psychiatric institutions in the 1950s and 60s. And at the time, there were much fewer regulations around human experimentation, especially in psychiatric institutions. So many of the patients were institutionalized against their will and may not have been in a position to fully consent. And today, these studies would raise serious ethical red flags. But back then, mental institutions were a gold mine for this kind of unethical human experimentation. So some of the things he was able to get humans to do and feel as a result of neurostimulation include pleasant sensations, elation, deep, thoughtful concentration, odd feelings, super relaxation, colored visions, and other responses. Delgado described a psychiatric patient who had electrodes implanted in a part of the brain that was associated with motor control and possibly also associated with reward or compulsion circuits. We don't always know for sure because he doesn't always specify exact brain regions in his report. But here's what happened. The patient was seated near a guitar, and Delgado activated the Stimoceiver, and he sent a signal to stimulate that specific brain area. And then the patient stood up, picked up the guitar, and strummed a few chords. And when he was asked why he did this, the patient replied something like, "I felt like I wanted to play the guitar, so I did." And this behavior was repeated each time the stimulation was applied, regardless of the patient's mood or the intention. And when the stimulation stopped, the desire disappeared. So this showed that brain stimulation created a strong compulsion to act, which the patient rationalized as his own free will. This supported Delgado's theory that electrical signals could not only trigger movement, but also influence the feeling of motivation or intention behind the movement. And that raised a very chilling possibility. Could people be made to act and believe that they chose it without knowing that they were being externally controlled? So Jose Delgado freaked a lot of people out with his book entitled Physical Control of the Mind Toward a Psycho-Civilized Society. Here are some choice quotes from that book. We are now in a position to induce changes in behavior by electrical stimulation of specific cerebral structures. The individual may think that his actions are the result of his own decision, but actually they may be determined by an external electronic influence. We need a program of psychosurgery for the political control of our society. The purpose is physical control of the mind. The human race is at the threshold of a new era in which it will be possible to control emotions, intellect, and behavior by electrical stimulation of the brain. So this is literally the dystopian nightmare version of what's possible with neural implants. The core of Delgado's vision wasn't curing disease or helping patients, but reshaping human nature itself for the control of society. Thankfully, as time went on, other researchers came along who envisioned applications for neural implants that are a lot less scary and dystopian. And that includes Eberhard Fetz, who was the first researcher to use brain signals to move a cursor on a computer. Not Elon Musk or Neuralink. Eberhard Fetz's work laid the foundation for brain-computer interfaces, and he was also the first researcher to experiment with closed-loop stimulation. So what is closed-loop stimulation or closed-loop neuromodulation as opposed to open-loop neuromodulation? So open-loop neuromodulation will just deliver electrical stimulation with no feedback. However, closed-loop modulation senses brain signals like the onset of a tremor or seizure, and then it will deliver a precisely timed stimulation to stop or modify that activity. So this system continuously monitors the effects, and it will adjust stimulation on the fly. And this has really great applications like Parkinson's disease. So in this case, the implant is going to detect abnormal beta rhythms, and it only stimulates when needed, which reduces side effects. This is really good for epilepsy. It identifies seizure onset patterns and intervenes before a seizure fully develops. It can also be used for depression and OCD, and these are experimental applications. But what happens is the device tries to detect mood states and applies stimulations to prefrontal or limbic areas accordingly. And this was a really big deal because it brought us closer to intelligent, responsive neuroprosthetics. So then, in the 1980s, Alim Louis performed the first chronic successful deep brain stimulation surgery to treat Parkinson's tremor. So let's talk a bit about what deep brain stimulation is. So in deep brain stimulation, you have these thin electrodes that are surgically implanted into target brain regions. And a pulse generator is implanted under the skin by the clavicles. And it's connected by wires that are tunneled under the skin up to the electrodes. So what happens is the implanted device sends high-frequency electrical pulses to the targeted brain area. And these pulses override or disrupt abnormal brain patterns of electrical signaling in the brain. And then after surgery, clinicians will program the device, and that means adjusting things like voltage, frequency, and pulse width. And people with Parkinson's disease have made some amazing strides in terms of quality of life with these implants. So Benjamin Stetcher is a great example of a person whose quality of life was significantly improved by neural implants. He was diagnosed with Parkinson's at age 29, and he had several impaired motor functions that severely inhibited his autonomy. And now he's a prominent advocate and educator for deep brain stimulation in the Parkinson's community. And I actually got to meet him. He came and talked to our research group. So I'm going to start this movie that he made, hopefully. Okay, let's start it right here.
I think so.
Can I use this? Okay, we're going to start it right here so that you can see this is before his DBS electrodes were on. It's kind of what his movement looked like. And he had his second reprogramming session. And then he found a sweet spot.
Looks pretty good, doesn't it? I think so. And more importantly, I think it feels really good. There doesn't seem to be any dyskinesia, and there doesn't seem to be any rigidity at all either. And there's also no tremor, from what I can tell. Maybe there might be a slight one, but whatever. Yeah, let's go for a little walk here.
Yeah, so that's a beautiful story. Obviously, his symptoms have significantly improved with this therapy. But what happens is he has to get his electrodes retuned every 3 to 6 months. And he said that when he gets his electrodes retuned, that can sometimes induce bouts of mania. And he admitted that he actually really likes this feeling of mania. And sometimes he'll lie about how the settings feel. And he said that one time he had such mania afterwards that he spent the afternoon walking around a park trying to convince everyone that he ran into that he should be the Prime Minister of Canada. So he was a pretty cool guy. He was very funny. I liked him. I enjoyed meeting him. Okay. Oops. Okay, so let's talk about the Utah array next. That was invented by Richard Norman from the University of Utah. The Utah array is a microelectrode array, and this is a device that's made up of tiny needles that can record and or stimulate neurons in the cerebral cortex. And this is just a 4 millimeter by 4 millimeter array of 100 needles that sits on the outside surface of your brain and just stabs into it. And the Utah array has been the basis for a lot of fundamental research, and it's proof that this technology can really perform. So John Donahue's team successfully implanted the first BCI device in a human using a Utah array. And that's brain-computer interface. So John Donahue has spoken passionately about giving agency and autonomy back to people who can no longer move or speak. And his work really shaped how we think about assistive neurotechnology, not just as a gadget, but as a human right. Speaking of implanting the Utah array, a man in Germany with advanced ALS has become completely locked in. He could no longer move any muscles, including his eyes, and he had no other means of communication. So researchers implanted 2 Utah arrays in his motor cortex, and then using brain-computer interface and auditory neurofeedback, he learned to modulate his neural firing rates to select either yes or no. And then, now that he has this binary system, he was able to select letters and spell out words very slowly, but it did work. And he was able to communicate the sentence, "I love my cool son," which is so beautiful. Matthew Nagel was another pioneering figure in the development of brain-computer interfaces. In June 2004, he became the first person to receive the BrainGate neural implant. And this device, consisting of a 96 electrode array, was implanted in his motor cortex. And that allowed Nagel, who was paralyzed from the neck down due to a spinal cord injury, to control external devices using only his thoughts. So with this implant, Nagel achieved several groundbreaking feats. He could move a computer cursor on a screen by imagining the movement of his hand. He was able to check and send emails and play simple video games like Pong and control his television all through thought alone. He also managed to open and close a prosthetic hand, demonstrating the potential for brain-computer interfaces to restore motor functions. So Nagel's participation in the BrainGate clinical trial provided invaluable insights into the capabilities of neural interfaces, and it laid the groundwork for future advancements in assistive technologies for individuals with severe motor impairments. Of course, there are some major downsides to this type of device, and one of them is that it requires this big, bulky piece of external hardware on the outside of the skull that's connected to a wire. And another problem is that it causes a lot of inflammation and scar tissue, which ultimately walls off the device and it stops it from being able to interact with neurons. So the way that researchers have been addressing those issues is to make the devices wireless and controllable via Bluetooth. And also, as I mentioned in the beginning of the talk, we also want to make devices that are small and flexible so they don't cause a lot of disruption in your brain tissue. But even if you have small devices that are the exact same squishiness as the surrounding brain tissue, implanting them in a brain still requires a craniotomy, which is a majorly invasive surgery involving temporarily removing a portion of the skull. This bone flap is removed so that they can access the brain. So, one company has come up with a very interesting solution for this. The Stentrode, which is developed by Synchron, is a groundbreaking brain-computer interface that doesn't require open brain surgery. Instead, you deliver the Stentrode through a blood vessel near the motor cortex. So you can even go in through the jugular vein and go all the way up to your brain. And it works just like a cardiac stent. It records brain activity from inside the vein. It's fully implanted and wireless, which allows people with paralysis to control digital devices at home using just their thoughts. The Stentrode is the first truly minimally invasive BCI to reach clinical trials. You can bypass brain surgery altogether because you just access the brain by entering through a blood vessel. The Stentrode started human trials in 2020 and it's already been implanted in multiple ALS patients, and it restored their ability to communicate. So this is Thomas Oxley here, the CEO of Synchron, and he shared a really compelling vision of the future of brain-computer interfaces in his TED Talk. He described the potential of brain-computer interfaces to enable individuals to convey their thoughts and emotions directly without using words. Like, think about how hard it is to tell people how you feel. Some people are really bad at doing this, and even for very expressive and articulate people, words are always going to fall short when it comes to describing exactly how you feel. So imagine being able to throw your feelings to someone else, even just momentarily, and have them understand exactly how you feel. So this could be the future of communication. We could bypass words altogether, and you just send signals wirelessly from your neural device to someone else's neural device. This is us enabling telepathic communication. And there's all kinds of futuristic, magical applications you can imagine with this technology. Like, imagine a game where you don't have to push any buttons, you just think your next move. And imagine how awesome it would be to play that game in virtual reality. There are tons of cool applications in cognitive enhancement. Like, you could use neural implants to monitor your brain states that occur when you're very focused or very creative or very insightful. And you can use machine learning to recognize those neural patterns and then recreate them synthetically via stimulation. So imagine if you were like, okay, time to be insightful, and you just pushed a button and suddenly you were focused and creative or whatever you wanted to be. Imagine being able to download a new language or skill by reinforcing the key neural circuits with precisely delivered stimulation. Imagine brain-based authentication, like your computer password or a key to your house is just a thought you have that unlocks it for you. What about bidirectional neural prosthetics? So of course, brain sends control signals to move a limb, right? And then the limb sends back touch and temperature feedback, which the brain interprets. So this loop could make robotic limbs feel real to the user. And the very obvious use case is people who are missing limbs. But what about new limbs altogether that we've never even thought about? Like, what about a long tentacle-like limb that you can use to feel around inside an area that you wouldn't otherwise be able to reach? Imagine unclogging your drain with that. Or what about limbs that aren't even attached to you? What about robotic bodies that allow you to touch and sense things that are on the other side of the world or on a different planet? What if you could integrate seamlessly with any machine that you want to control? Like, what if you could drive your car with thought alone, or control a remote spaceship with thought? What if you never lose your phone again because you can just tap into the GPS location of your phone with thought? Or what if you don't even need a phone anymore because all of the functionality of a phone and computer is already built into your neural implant? Or what if a neural implant could control your motor functions and you could remotely control someone else's body with your thoughts? What if neural implants make diagnoses better because your psychologist could experience what you were thinking and feeling without you having to describe it to them? What if your neural implant could integrate with your AI assistant? Imagine just sitting in an airport and having a mental conversation with ChatGPT, just wondering about things and immediately accessing answers. Or using ChatGPT to come up with great comebacks for you or great counter arguments. So I could brainstorm cool applications for neural implants all day. And I'm really hoping this is what we do for most of the Q&A session. So I will wrap it up with this. Neural implants have a long and storied history. They were born from curiosity, shaped by science fiction, and now they're transforming lives in reality. What began as experimental brain stimulation has evolved into powerful technologies that restore communication, movement, and even memory. As we look ahead, these tools hold promise not only for helping those with disabilities, but for enhancing what it means to be human. Of course, with great power comes profound ethical responsibility. The hope is that our sense of wonder and compassion will guide us so that this technology becomes a force for inclusion and empowerment rather than division and control. Thank you very much.